Hi, everyone. And thank you, Kim, for the invitation. Thank you, Julie and Wande, for your great talks. So the question I want to address today is what is the longevity of these beautiful border faults that we've seen in the previous talks? What controls that longevity? And I'm going to start with a broad review of some models that have been put together over the years, and then transition to new results, specifically focusing on the role of surface processes and crustal rheology. So by border fault, I mean these massive crustal scale normal faults that accommodate and really dominate the extension in continental rifts. And slip on these faults typically leads to significant flexure of the footwall and hanging wall, which interacting with surface processes shape footwall range and hanging wall basin. And those structures are known as half-grabens, and they're really the building blocks for most continental rifts. So you can think of arranging them in series and form a wide rift, like in the basin and range, here on the top part of the slide. Or you could assemble them, so to speak, in parallel to straddle the axis of a narrow rift, like, for example, in Lake Malawi. And as we saw in Julie's talk, understanding how much offset can build up on each of these structures is essential, because it could lead to massive consequences for the structural makeup of the rift. So here's, for example, an out-of-control border fault that has accumulated tens of kilometers of offset to shape one of these beautiful turtlebacks, metamorphic core complexes, in this case, the Whipple Mountains. So my question is, how much offset can we build on the border fault before strain localizes elsewhere? So in a place like Lake Malawi, that might look like forming a new border fault in the basin. Maybe that will happen in the future. That's certainly been documented in the Aegean. Or it could also mean localizing a new dominant fault in the footwall, maybe forming a horse structure, as we can see, for example, in the Rwenzori Mountains. The approach I'm going to follow today is that of the lazy earth hypothesis. The idea will be that border faults will remain active as long as it's the lowest energy configuration, as long as it's the laziest thing to do. So with my talk, I'm going to review some factors that oppose border fault slip and understand what might lead to their abandonment. I'll start with rotation, then get into a little bit of fault block flexure, and then specifically talk about the growth of relief and the impact of the lower crust. So the earliest models of fault evolution and deactivation date back to Anderson, and they postulate that the principal stresses are horizontal and vertical. In the rift, you might think of them as a combination of lithostatic compression and some component of horizontal deviatoric tension, delta sigma. And if you assume that the bulk friction of intact crust is about 0.6, then you can map the differential stress, this tension you would need to apply to the crust to break a fault. So that would be the black curve on the right. And you can see that it's minimized at a dip of about 60 degrees. So let's say you do apply that stress, you break that fault, it's the least stress configuration. You're at the black circle. And then immediately as you form a fault zone, you might assume that you lose most of your cohesion. So that moves you to the red circle on the red curve. But then another thing that might happen is that as you accumulate finite extension, your fault might rotate to shallower angles. So this could happen, for example, through bookshelf faulting or through other mechanisms related to finite extension. And in that plot on the right, this would mean that you would be moving along the red curve, along the red arrows, and the stress that it would take to keep the fault active, to continue slipping on the fault, would increase as you rotate to a shallower dip. When you encounter the red star or the flat dashed black line, you might actually require more stress to keep your fault active than to break a new fault in intact crust. So in that case, it would be more favorable to break a new steep fault than to continue slipping on your rotated border fault. Another thing that might happen as you approach angles close to 30 degrees is frictional lockup, meaning that the horizontal tension you would need to keep your fault active would exceed the lithostatic stress, and you would need net tensile horizontal stretch, which is not sustainable in the continental rift. So all this to say that in this classical Andersonian view of faulting and rotation, normal faults that reach dips of about 30 degrees should be deactivated. But there are limitations to this approach, mainly related to finite extension and the onset of flexure of the footwall blocks. So I'm illustrating this with a simple numerical model of a steep fault in a perfect elastic brittle layer that's 15 kilometers thick, on which I'm pulling and extended by about 6 kilometers. So you can see two things. The first is that as I accumulate offset on my red fault here, I warp my footwall and hanging wall. I lower its dip from 55 to 47 degrees through flexural rotation. And the other thing that happens is that the principal stresses do rotate close to the fault, and they are no longer Andersonian. So this really suggests that flexural effects could modulate the optimal dip of normal faults as well as their long-term evolution. So this is something that's been studied by several authors, starting with Don Forsyth in the early 90s and then Roger Buck. And they asked how the flexural properties of the crust would modulate the longevity of border faults. The idea can be summarized as a force balance concept. So think about the force you need to apply. Think of how hard you need to pull on the crust to keep your fault active while accounting for flexure. So part of that force or that energy is spent overcoming the frictional resistance on the fault. And part of that force will serve to accumulate bending or sustain the cumulative bending of the fault blocks. So that would be the blue curve on this plot, which increases as a function of fault offset. If you sum these two force contributions as a function of fault offset, you will find that initially you get a drop in the force needed to sustain slip. That's just fault weakening, loss of cohesion, for example. But then you get an increase, which relates to the accumulation of flexure. And at some point, you might again reach that threshold where it's easier or takes less force to break a new fault elsewhere than to sustain slip on your initial border fault. So if you do this in a weaker or thinner faulted layer, whoops, I skipped a few slides here. If you do this in a thinner faulted layer, you might find that bending the fault blocks will not lead to a particularly strong increase in force. And in that case, the total force needed to sustain slip might remain below the threshold to break a new fault. So that's a case where your border fault can grow essentially forever, and you could build a detachment of one of these metamorphic core complexes. So that framework has been fairly successful at explaining why we tend to see these very large offset faults in settings that tend to have thinner brittle layers. For example, mid-ocean ridges or the Basin End Range or the Aegean domain, as opposed to colder, thicker, narrow rifts, for example. So one aspect of flexure that hadn't been too carefully looked at before is the building of relief. That's something that we started to study a few years ago, specifically asking the question of, well, as you flex the hanging wall and footwall, you're going to build topography, and you're also going to grow a basin. And these things have an energy cost if you think of gravitational potential energy. Both building a positive and a negative relief amounts to storing gravitational potential energy in your system. So that's price to pay, which should oppose the prolonged slip on border faults. So back in 2014, we modeled this, again, in simple, ideal brittle layers overlaying a weak lower crust. These snapshots show these types of layers on which we pull. We extend them by about 22 kilometers, initially seeding a single blue fault. And what we found is that if we completely suppress the growth of relief, we can get the border fault to be active forever. Whereas if we let the relief grow unaltered, the border fault will be abandoned in favor of a new one, et cetera, and we'll get short-lived half-grabens or eventually forming a host structure. So that was interesting because it opened the possibility that erosion and sedimentation surface processes might modulate the maximum offset on border faults. But the question that remained after this paper was, well, can erosion in real Earth conditions be efficient enough to impact those systems? And would this hold when we consider a more realistic rheological profile for the crust? So to address these questions, we put together these fully coupled models of border fault growth interacting with landscape evolution models. So representing mainly the incision from rivers and the infilling of basins. And the results I'm going to show have been published earlier this year in PNAS. Basically, what we did is vary the efficiency of river incision and the various strength profiles in the crust from a hot, weak end member on the left all the way to a cold, brittle and strong lower viscous crust on the right, simply by changing the geotherm.
You're now at 10 minutes.
All right. So what we did again is seed a border fault, let it grow a little bit, subjected to these varying degrees of river erosion in various rheological profiles. And let's look at what a beautiful half-graben like this becomes in these simulations. So I'm going to show you what happens when you vary crustal strength and the efficiency of erosion. First, if you grow this half-graben in a fairly strong crust, what we found is that after about 8 kilometers of throw on the initial border fault, strain tends to relocalize in the footwall and form a synthetic and an antithetic fault, eventually forming a horse-like structure. We refer to this regime as footwall snapping. But if we do this, if we do this in weaker crust, we get a fairly similar result. After about 6 kilometers of throw on the initial border fault, we get these footwall snapping structures. By contrast, if we up the intensity of river erosion within a realistic range, because we're now using surface processes models that have been calibrated on real systems, so this is reasonable. If we up the intensity of erosion, what we found is a profound impact on the modes of strain relocalization, this time forming a new border fault in the basin or the hanging wall of the initial border fault after 10 kilometers of vertical slip. And we found more complicated regimes in weaker crust with faster erosion, with faults forming on both sides in that case. So in this plot, I'm showing you the total fault throw that has accumulated on my initial border fault as a function of the efficiency of river erosion. So these are the 3 colored bands. The blue one is for the strongest crust end member. The red one is for the weakest crust end member. And you can see that they all increase with the efficiency of erosion. The rectangles show you real sites, so real half-grabens, some of them active, some of them potentially abandoned from the Basin and Range and the East African Rift and the Taupo Rift in New Zealand. They're also color-coded by our estimates of crustal strength. And what's interesting is that they're all bounded by this upper limit at about 7 kilometers of throw. So our models do a reasonable job at giving us a reasonable upper envelope for the total throw on these border faults. And we do see that erosion increases the lifespan of these border faults in a fairly significant way. We can increase it by as much as about 30%, especially in weaker crust. What might be somewhat surprising, though, if you remember the previous results, is that now the effect of strength seems to be reversed, because we saw border faults that accumulated greater throw in the stronger end member than in the weaker end member. In other words, the blue band is above the red band in this plot. So this might have to do with differing dynamics of rotation, which means fault throw is not related to fault heave in exactly the same way in all these simulations, or it could reflect a defocusing effect of the viscous lower crust that we have yet to fully understand. So to wrap up, I will summarize the many ways that you can kill and abandon a border fault. The classic way would be to let them rotate away from their optimal orientation. But it is important, as I've shown, to consider the finite extension and flexure of the blocks that they cause. So faults that grow in hard to bend, really strong or thick brittle layers tend to build up lots of flexural stresses, which drive the delocalization of strain. And the buildup of relief, both positive and negative, is an important part of that picture, because it constitutes a significant energy cost that surface processes can alleviate or not alleviate. So if you have very inefficient erosion locally and you grow lots of relief, you're more likely to snap your fault footwall and turn your half-graben into a horse, at least in our simulations. And the last point is something that we're exploring now, focusing mainly on mid-ocean ridge examples, is the fact that if you grow above a strong viscous lower crust or lower lithosphere, you will get a strong defocusing effect on the dynamics of these border faults, possibly in a strain rate dependent manner. Also effects related to the thinning of the moho, which influence the evolution of border faults in a non-trivial way. So we're working hard on this, and stay tuned for results in complex rheologies. Thank you.
Thank you so much, Arthur. It was a lot, and really makes seismic interpretation feel a lot harder than it should be. But again, a good reminder that these surface processes need to be considered, because they can have such a driving effect. Are there any questions for Jean-Arthur? Either put your hand up or put a question in the chat. Oh, come on, we've had such a questioning group. Oh, there's a question from Derek. Derek, go ahead.
The question is, when you're comparing the models to the natural examples, how does the pattern of the fault relocalization compare, like whether it's forming on a hanging wall or footwall? Because you showed the maximum offset, how that compares, but yeah.
Great question, gives me the opportunity to show my backup slide. So this is a regime diagram from our simulation with the efficiency of erosion on the x-axis and a proxy for strength on the y-axis. And here we've color-coded the real examples by the regime that we might be seeing in the field. So the first thing you should see here is that in these rifts that have a brittle crustal thickness between 10 and 15, all these gray rectangles, these are all basin and range. And they do tend to be mostly dominated by footwall snapping. So fault localization in the footwall of an initial border fault, something we see, for example, in the Ruby Mountains in the basin and range. By contrast, if we look at the stronger crust end member, which could be the East African rift, we see that a system like Malawi, which has a very thick brittle crust, in fact, thicker than the lithosphere, the brittle lithosphere thickness is even thicker than the crust from the depth of earthquakes. We see that this is a regime that would be more conducive to breaking in the hanging wall. So maybe that's what we're seeing now with this pattern of seismicity, although it's impossible to tell with the short window of observations. And this other end member that I plotted here is the Rwenzori's, which is a horse block that completely stands out in the western branch of the East African Rift. And that might be related to the fact that for some reason, relief managed to grow, or very significant relief managed to grow there. Perhaps because the gneissic basement that's exposed is hard to erode. And at least in our simulations, if you let a lot of relief build in a strong crust, you will end up with a horse structure. Sorry, that's a very long answer to your question, but it does roughly match at least what little observations we have. And if you have, if you know of other sites that could be compared, it would be super helpful to discuss this.
Thanks. Yeah, I'll give some thought. Brilliant.